Hi everybody, welcome to my video on the third part of the completion metric spaces topic. So the statement that we're trying to address is this. For a metric space X, there exists a complete metric space X hat which has a subspace W that is dense in X hat. The space X hat is unique up to isometries. Okay, so in this video we prove that X hat is a complete metric space. That is, every Cauchy sequence in X hat converges to some element of X hat. And we also prove that X hat is unique up to isometries. Okay, so without further ado, we now prove the completeness of X hat. Okay, so let Xn hat be any Cauchy sequence in X hat. As W is dense in X hat, i.e. the closure of W is equal to X hat itself, every open ball centered at Xn hat in X hat of radius r bigger than 0 contains some Zn in W, or Zn hat in W rather, such that the distance between the points Xn hat and Zn hat is always strictly less than r. So in particular, for the radius 1 on n, where n is in n, we can clearly say that r, for this choice of r, it will always be bigger than 0. And we know that there exists some Zn hat in W, such that the distance between Xn hat and Zn hat will always be strictly less than 1 over n. So our first claim here is that Zn is a Cauchy sequence. So by the triangle inequality, we have that the distance from Zm hat to Zn hat is less than or equal to this expression here, which is then less than or equal to this expression here by using the above fact given here. So as Xn hat is a Cauchy sequence, we know that for all epsilon bigger than 0, there exists some big N in the natural numbers, such that the distance between Xn hat and Xn hat is always less than epsilon 1 over 3 for all n and m bigger than big N. In particular, we can choose our n in the natural numbers such that n is bigger than 3 over epsilon. So we now use this to construct the formal proof that Zn hat is a Cauchy sequence. So we let epsilon greater than 0 be given, and we choose n in n in the natural numbers as before. Then, for all n and m bigger than big N, the distance between Zm and Zn is given by the same expression as before, which is less than 1 over capital N plus epsilon over 3 plus 1 over capital N, since little n and little m are both bigger than capital N. This in turn is then less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon. So what we have shown is that Zn hat is indeed a Cauchy sequence. Now, from the previous videos, we know that the mapping from T from the space X to the subspace W is an isometry. And we also know that, well, this Zm hat is in W. So we have that the sequence Zm, defined by Zm, is equal to the inverse of the mapping T acting on Zm hat is Cauchy in X. So we let X hat in big X hat be the equivalence class to which the sequence Zm belongs. So what we now want to show is that the limit of Xn hat is X hat. So again, by the triangle inequality, we have that the distance between Xn hat and X hat is less than or equal to the distance between Xn hat and Zn hat plus the distance between Zn hat and X hat, which in turn is less than 1 over n plus the distance between Zn hat and X hat, using the property that the open ball of radius 1 on n centered at X hat, Xn hat in X hat is and then that distance to Zn hat is always less than 1 on n. Okay, so as Zm is a sequence in the equivalence class X hat, and Zn hat is in W, we know that the constant sequence, Zn, 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 that keeps on going forever, is in Zn hat. So the previous inequality becomes the distance between Xn hat and X hat is less than 1 on n plus the limit as m approaches infinity of the distance between Zn and Zm, where the last distance is now using the metric on X. But we know that Zn is Cauchy. So precisely that means that for all epsilon bigger than 0, there is some capital M in the natural numbers, such that the distance between Zn and Zm is less than epsilon 2 for all n and m bigger than capital M. Whatever. In particular, there exists some capital M in the natural numbers such that m is bigger than 2 over epsilon, and the previous statement holds. So now we let epsilon bigger than 0 be given, and we choose our capital M in the natural numbers such that m is greater than 2 over epsilon. Then for all n and m bigger than m, capital M that is, we have that the distance between xn hat and x hat will be less than epsilon by this reasoning here. So what this shows then that xn hat converges to the limit x hat in capital X hat. So in particular, so we have shown that the Cauchy sequence xn hat converges to an element of capital X hat, and so x hat is indeed complete, as desired. We now prove the uniqueness of x hat up to isometries. So we have the sort of following pictorial depiction of the scenario here. We start with our space, metric space X. We apply some mapping T, and it takes us to a subspace W equals to T of X. T applied to X, such that W is dense in X hat. Similarly, we can also apply another mapping T tilde that takes our space X and turns it into a subspace T tilde applied to X, and the subspace W tilde is dense in X tilde. So what we suppose is that X tilde, D tilde, is another complete metric space that has a subspace W tilde dense in X tilde, and that W tilde is isometric with X. Then, for all X tilde and Y tilde in X tilde, there exist sequences xn tilde and yn tilde in W tilde, such that xn tilde converges to X tilde and yn tilde converges to Y tilde. So from previous videos, we have that the following inequality. And now this the right-hand side of this inequality goes to 0 as n goes to infinity, since xn tilde converges to X tilde and yn tilde converges to Y tilde. Yep. And then as W tilde is isometric with, well, X and hence a subspace W of X, and W is dense in X hat, i.e. the closure of W is equal to X hat, we see that distances on X tilde and X hat must coincide. In other words, X tilde and X hat are isometric with one another. And indeed, X hat is then unique up to isometries as required. Done.